as was said, I am Abigail Frost, and I'm going to be talking to you today about the work that I did during my PhD, where I used a combination of infrared observations to study the circumstellar environments of massive young stellar objects and investigate their disks. So this work was done at University of Leeds, but I'm currently at KU. Okay, so we've heard a lot of great talks today already talking about low mass disks, so T-Tauri disks and her big AE and EE disks. And for those objects, we have a really nice kind of picture of how the disks evolve and how how you get from that molecular cloud to that potential planetary system. And we've now observed all of the phases that you can see listed in this cartoon that I made here. We have observations for almost all of these phases. However, for high mass star formation, that is for stars that have initial masses of greater than 8 solar masses, our picture of this formation process is much less well understood. And this is due to the additional observational limitations associated with studying massive young stars. They are deeply embedded in nature. They tend to be rarer than low mass stars, and also tend to be more distant than low mass stars, which has made them more difficult to study. In particular, the later stages of the massive star formation process are yet to be constrained. We know that they form from a giant molecular cloud, and we see massive cold cores. And we've started in the last decade or so to detect disks around massive young stellar objects within their envelope and when their envelopes. But it's how these disks evolve and what happens to the disk past the earliest stages is still yet to be constrained. And essentially what I did is I combined a variety of different observables in order to study the environments of MYSOs at different scales. And I applied this methodology to a group of MYSOs so that we could compare what we find about MYSOs and their disks to each other in a consistent way. So these are the 3 observations that I used. The first one is interferometry. This is taken between 7 and 13 micron in the M band by the MIDI interferometer at the VLTI, which has since been decommissioned, with a maximum resolution of 0.01 arcsecond scales. The second observation that I used is imaging. This is at around 20 micron in the Q band, taken with 2 different instruments, Vizier at the VLT and COMEX at the Subaru telescope. And the resolution of this data set was 0.1 arcsecond. And finally, I also used an SED. So this provides you with multi-wavelength information from near infrared to millimeter wavelengths and traces the entirety of your source, but doesn't provide any direct spatial information. So it's important that you combine the SED with some kind of spatially resolved observations so that you know exactly where your emission is coming from. And essentially what I did was I fit one radius transfer model generated with HoChunk 3D, a code by Barbara Whitney, and I found a fit to all of 3 observables using one model so that the geometry of the MYSOs was constrained at multiple scales. And so by doing this, I was able to find out the following. So we found that the infrared interferometry is particularly sensitive to emission from the inner disk regions in these sources, and also the innermost cavity emission. We find that the Q-band imaging is most sensitive to emission being radiated from the cavity walls at larger scales because of the change in temperature, and is also sensitive to the envelope infall rate, because if your envelope is rotating and infalling, it's pushing material towards the center, which then eventually falls to disk. And so the amount of envelope infall that we had was something that could be picked up in the Q-band image, where you're piling up all this cold dust to feed into eventually the disk. And the SED was sensitive to, as I said, the entire protostellar environment. Now you'll notice that we had 2 observables that trace cavity wall emission. And because we have this in place, we were able to distinguish between disk and cavity emission for these sources, because you have a kind of a double constraint, if you like, on the cavity geometry. You can't just kind of change that to fix your, to fit your MIDI data and your Q-band data. And we found that essentially, in order to satisfy all the observables, we had to include a disk in these models. And because we could separate between the 2 kinds of emission, we were able to probe the disk in more detail. So this is kind of a collection of plots to help illustrate this. So on the right, you can see radial profiles derived from the model and the source images, for this case with Vizier, on the right in the top. And then just below that, you can see an SED fit for one source as well. And on the left, we have 3 different fits to MIDI data. And each of these different models provides the same Vizier and SED fit, because these data sets are just not tracing the small scales where MIDI is sensitive because of this difference in revolution between the data sets. So it's really important that you have this high resolution data to look at the fine details of the environments that you're looking at. And so you can see in the top, we have a model which has no disk, and you can see that's very, very badly fit to the data. In particular, it's not replicating that upturn in visibility that we see between 7 and 9 micron. And such an upturn indicates that you have you're not resolving something, that you have a less resolved component that you're not seeing. And a compact component that could be potential was a disk, so we added a disk to the model. And we see that this upturn is now recreated, but also the fit still isn't very good. And ultimately what happened is that in order to provide an adequate fit to the data set, we had to introduce clearing in this disk. We had to remove dust between the dust sublimation radius of the star, or the central object rather, and a larger radius. And that implies that something is disrupting this dust in the source within the innermost disk regions. And so I essentially went through analyzing data sets like the ones I just showed for a sample of MYSOs, and then I was able to compare the characteristics that I obtained for these sources within the group. So we found that they all have similar overall geometry. They're all disk, envelope, and outflow cavity systems. The types of the envelopes are Ulrich type. So we found that rotating and infalling envelopes are the best fit to the data that we see, with typical inflow rates of 1 × 10⁻⁴ solar masses per year. We found that while there's a variety in the densities and the opening angles of these cavities, they're all similar shapes. And we find quite a bit of variation in the disks. We find some flat disks, we find some flared disks, and we find that substructures like this inner hole of 68U, which I mentioned previously, were present for a number of the sources. We found various sizes of inner holes, so various cleared regions in these disks. And we also found one source, which you can see illustrated on the right here, which shows a gap-like structure. And this was introduced using the spiral capabilities of the radiation transfer code. It's essentially a very, very mass-heavy, very loose pitch spiral.
Abigail, you have about 2 minutes left.
Thank you. And so once we had these geometrical characteristics for the source, we decided to see how these might fit into an evolutionary sequence. And such a sequence was derived for MYSOs by Heather Cooper in 2013. She looked at the near-infrared spectra for a large group of the MYSOs, and she saw that various emission lines that you can see listed here changed depending on the types and she could then group them into types rather. So type 1 here are the youngest and type 3 are the eldest. And we looked at the spectra for all of our sources and classified them according to these types. And we found that all of the disks with these inner holes or this gap substructure were type 3 objects. So they were the eldest sources according to this classification. And what's also interesting is that for the type 3 sources here, one of the key lines for determining whether your MYSO is a type 3 evolved source is fluorescent iron 2, and its presence basically implies the presence of UV photons. So this might suggest that these gaps that we're seeing in the massive young stellar object disks could be due to a photoaberration, or at least that could be a contributing cause. We also found that the type 3 sources had wider cavity opening angles, and this through comparison with work with Stella Offner in 2010, who saw that through modeling the cavity opening angles of MYSOs get wider with age, we were able to put numbers to these based on the values we got for our cavities, and we find that all the type 3 sources are around 1 to 5 times 10⁴ years. So despite the very fast formation timescales that are associated with MYSOs, we're still seeing suggestions of substructure appearing, and that is marks similarity to kind of low mass disk evolution. So it's interesting to think whether this might be occurring for MYSOs as well. And with that, I will leave you with my summary, and I will now take any questions.